Assalamualaikum warahmatullahi wabarakatuh. Thank you, ladies and gentlemen. So today we would like to present our work, the title MPS Method Simulation on Shockwave Propagation of Dam Break over a Wet Channel for Severe Accident Reactor Investigation. My name is asril Pramutadi from ITB, our team, Yakobus Yulianto and Rizky Arbi. So this is the contents. We start with the introduction, objective, approach of the study, results, and discussions and remarks. As for the introduction, nuclear power plant, its severe accident, may melt the structural materials at different temperature. These are the overview of the reactor building. This is the reactor building. We have the reactor pressure vessel in the middle, the steam generator, we have the pressurizer, and we have the core catcher. This reactor pressure vessel is the place where we put the fuel of the reactor. That's where the fission reaction occurs. And after the fission reaction occurs and continue react, then the coolant from water for this for the conventional reactor start to form the steam by using this steam generator, and the steam generator will continue to the steam turbine and produce electricity. During the severe accident, this fuel, uranium dioxide, the temperature of the fuel will increase sharply, increase also affecting the surrounding materials. As we know, inside we are having a lot of structural materials, not just the fuel, but also the structural materials, for example, from zircaloy, from stainless steel, from steel, that may melt or having melting point with a different temperature. Metallic, for example, will melt at 1500 degrees C about, while the fuel oxide at 2300 degrees C. Moreover, we have the possibility of having eutectic reaction whenever we have two materials contact surface to surface that having the characteristic of eutectic reaction from the binary phase diagram. Then we will have the two materials melts at very low temperature in comparison to its melting point. So in that case, also we have the possibility, for example, from the figure, let's say we have the breaching of the RPV, and then the liquid inside or the molten materials start to flow to the core catcher. So we have the possibility that we will have the molten metal first exist on the core catcher, and after that followed by the fuel, molten fuel, corium. So based on that, the objective of this study is to simulate the two interaction or the interaction between the wet channel with the following molten materials. So this study like to simulate the experimental reference result of shockwave propagation of dam break over wet channel by using MPS method in the geometry. And this is as the first step before we investigate in advance to the investigation of severe accident of the. Okay. So as for the simulation MPS, the moving particle semi-implicit originally developed to simulate incompressible flow by Professor Koshizuka from Tokyo University in 1996. It's fully Lagrangian description, particle-based domain discretization, and massless method, unlike the method that usually being used for computational dynamics. And it's capable of dealing with free surface because it's naturally track the particle or the liquid and with the mass conservation, and also dealing with the complex geometry, multi-bodies, large displacement, large deformation, especially because in the severe accident of the nuclear reactor, we will have a lot of case of large deformation. Also dealing with fragmentation, merging, multi-phase, and multi-physics. The governing equation of this MPS is the mass conservation and the momentum conservation. Mass conservation using this formula and momentum conservation using this formula, or the so-called Navier-Stokes equation. Non-numerical diffusion due to the advection terms, differential operators derived from particle interaction model. As for the particle interaction model, we will use the weight function. The analogy can be seen from this figure. The calculated particle is the I particle, and then the I particle has its own effective radius, RE, and that's RE is defining whether the a particle is neighboring particle of I or not. Inside this radius, it's the neighboring particle, J particle. Outside, it's not the neighboring particle, and forms in this formula. If it's inside the radius, effective radius, then the calculation will be RE divided by R minus 1. If it's outside, then it's automatically 0. As for the scalar function psi, the gradient and Laplacian at the particle I are calculated using this formula. The first one is the gradient. This is the weight function, and this is the unit vector and the gradient calculation. And we have the D for the dimension. For example, 2 dimension, we put 2, or 3 dimension, we put 3. P and D is the particle number density calculated using this formula. And this is the Laplacian equation, the I particle. As for the boundary condition and algorithm, boundary condition, we will have the rigid wall. Rigid wall, from this case, these are the rigid wall. Okay. A no slip condition, rows of different type of particles describe the geometry. Free surface also, we have the fluid particle calculated with the calculating the free surface. Particle with the smaller will be defined as free surface 1. The pressure of all free surface is the atmospheric pressure. Solution algorithm of this method divided in parts: explicit and implicit. Explicit calculation of the external forces and estimation of the velocity and position of the particles, while implicitly the calculation is for the solution of a system of pressure Poisson equation. And these are the algorithm, the MPS method. And this is the case of the study. This figure from the reference showing the red color of the reservoir fluid and the yellow color of the downstream fluid. They are the same materials, salt water, even though in different color, just to show difference between a reservoir and the downstream. And these are the schematic figure. The reservoir, the height of the reservoir fluid is showing by H0, 0.15 meters. And as for the fluid for the downstream, showing by HT. And we have 3 cases vary within the HT using this formula. So we have alpha equal to 0.1, 0.4 cases. The result will be presented by HT graph using this formula. This is the viscosity, and this is the water salt density. Okay, as for the result, we start with the result of the case of alpha 0.1. This figure is from the experiment. These are the simulation 2 dimension. As we can see, once the gate in between is replaced or removed, then the water from the reservoir start to push water in the downstream, and water from downstream start to force or resist the water, and the formation of wave start to form. So you can see here, start to build up, and start to move with velocity. It's similar case. The MPS method shows the similar case formation of the wave with the almost similar speed. However, the MPS underestimate the formation of the waves, probably due to the resolution of this or small or a bigger particle radius, particle size that being used for the simulation. And this still the same case, but this sequence is the sequence just before the impact of the waves into the downstream wall, and after the as we can see, once again, the MPS can simulate similarly with in comparison to the experimental result. However, it's underestimate the formation of the. These are the graph of the sensor P1 and P2. The blue one is the MPS, the orange one is the experiment. So we can see that it is in good agreement with the simulation, or the simulation shows good agreement with the experiment. As we can see here, start to increase, then increase, and at this point. Similarly to P2, even though at some points there is a small discrepancy in this case, but not so. As for the case of alpha 0.2, after the gate was lifted, we can see that the reservoir start to push, but in this case, because it's higher than the previous case for the fluid in the downstream, then what happened is that the fluid in the downstream start to push back or resist the water from the reservoir, and that makes the formation of the wave. You can see the formation start at this time and build up, and then start to move. The wave start to move with a slower velocity in comparison to the previous study, because or the previous case 0.1. And the MPS method once again can simulate the formation of the wave with the similar velocity. However, it still underestimates the formation of the similar case. For this one, the velocity is similar, but the formation of the wave is underestimated by the MPS. This figure shows the sensor P1 and P2. As we can see that in the beginning, MPS method for P1 shows similar result or good agreement. However, after that, at some points, it shows disagreement, or somehow underestimate the height. And in this case, at this point, it's underestimate the height, and at this point also, but overall, it shows similar or good agreement. As for the alpha 0.4, meaning that we have more water in the downstream, it shows more force, resistant force into the water in the reservoir. But still, we can find the formation of of the wave with slower velocity, smaller value of velocity. So you can see here, MPS still can produce the same result. However, it underestimates once again the formation of the waves. This is also the same case as the previous. The formation of the wave is simulated, but the MPS underestimate the formation. Similar case occur for the after the impact with the downstream wall. From here we can see the sensor showing the good agreement, even though at some point this agreement occurs, but overall we can see good agreement. And the disagreement may be improved by using smaller particle size, meaning it's more detailed. However, the calculation time may be more, of course. And also the good agreement will be approached or will be obtained probably by using 3-dimension in this case. So from that we can conclude that in the present we can we simulate the 2D case for the dam break over wet channel, and then the effect of the differential water levels gives different potential energy and affects the speed of the wave front and the wave flow pattern and water depth predicted by MPS method agreed well with the experimental result. However, some discrepancies or disagreement may occur due to low resolution of the particle size and the 2-dimension case. And I'd like to thank you, P2MI 2022 program from ITB for funding this investigation or this study. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.